Hi, and welcome to my video. Here I'll be explaining how to find the function for stereographic projection along with its inverse using the line parameterization method. Another common method for this projection uses laws of similar triangles, but in this video we'll be parameterizing lines instead of using ratios. Let's start off with a unit sphere which has a radius of 1, and let's also place its center at the origin in R3. The sphere can be off-centered or not have unit radius if you'd like. Let's now list some more given information. We're gonna let n equal the point on the sphere 0, 0, 1. This point can be placed wherever you'd like on the sphere. However, I'm choosing the North Pole for simplicity, hence the given name n. I'll even keep the directions of the standard positive x, y, and z axes in R3 off to the side to make things a little more clear as to where the positive coordinate directions point. Let's now place an xy plane at the bottom of the sphere at height z equals -1. The only rules that this plane must abide by are that it should be perpendicular to the line that runs through n and O, and it must intersect the sphere at some place other than n. Here I drew a 90-degree angle in green between the line through n and O and the plane to indicate the perpendicularity. I also labeled the south pole to indicate that the plane meets the sphere at that point. Many people like to position the plane so that it slices through the sphere's equator. Both options are perfectly valid. Going back to the givens, we'll now let a point P equal some arbitrary point on the sphere defined by Cartesian coordinates P1, P2, and P3. This point P lives on the sphere, not within it. This means that the sum of the squares of P's coordinates must equal 1. Therefore, P1 squared plus P2 squared plus P3 squared equals 1. Finally, our last given is that we're going to let the point Q equal the point in the plane defined by Cartesian coordinates Q1, Q2, and -1. Point Q is where the line that runs through n and P intersects the plane. Notice how we gave it a last coordinate of -1. This is because it will always live in the xy plane whose z coordinate is locked at that fixed value. Alright, so here's what we'll be finding. Part 1. By parametrizing a line, show that the stereographic projection function f of p equals q, which maps the point P on the sphere to the point Q in the plane as shown in the diagram, is defined as follows. Part 2. Also by parametrizing a line, show that the inverse stereographic projection function g of q equals p, which maps the point Q in the plane to the point P on the sphere as shown in the diagram, is defined as follows. To make things a bit easier to understand, for the forward function in part 1, we simply plug in point P, and then the output is point Q in terms of point P. Likewise, for the inverse function from part 2, we simply plug in point Q, and then our output is point P in terms of point Q. Alright, let me clean up the screen a bit. Now you can see what is given and what we want to find at the bottom left corner. Finally, here on the right hand side is where we're going to start the solution for part 1. I've broken up part 1 of this exercise into 5 easy steps. Remember, to project the point P, our goal will be to find Q in terms of P. I'm going to let step 1 be to first treat the points n and P as vectors. It's useful to think of them this way when using the line parameterization method. Therefore, we can think of our points n and P now as vectors n and P, both defined by the same Cartesian coordinates. Here are those vectors on the diagram. As you can see, they both have their tails positioned at the origin O and their heads positioned at the original points. Step 2 will be to form a direction vector D with vectors n and p. When we go from the sphere to the plane, this vector must be between n and p, not n and q, because remember, we need q in terms of p. To form this vector, think about what bridges the gap between vector n and vector p. What must we add to vector n to equal vector p? Well, the answer turns out to be vector p minus vector n. If you cancel out the two vector n's, you can see why this is true, because we get vector p equals vector p. So, let's let our direction vector d equal this difference between vectors p and n. Here's what it looks like on the diagram. As you can see, it's parallel to the line that runs through the heads of vectors n and p. You may have thought that vector d should have been positioned up 1 unit, literally bridging the gap between the heads of vectors n and p. However, the catch to it is that vectors naturally have their tails positioned at the origin. One quick thing to mention is that this difference between vectors p and n is also commonly referred to as vector np. Another thing I feel the need to to mention is that we could have just as easily gone the other direction and asked ourselves, what must we add to vector p to equal vector n? And then have gotten vector n minus vector p, which can also be expressed as vector pn. Both routes produce vectors that are parallel to the line that we intend on forming. The only difference between them is that their directions are opposite of each other. They're both perfectly acceptable. However, I'm going to choose to keep the direction that points downward. Let's now solve for vector d by plugging in vectors p and n. Therefore, vector d equals p1, p2, p3 minus 0, 0, 1. This then reduces to p1, p2, p3 minus 1. I'll now erase some other stuff to reduce clutter, and I'm going to keep our direction vector at the bottom of the screen so that we can use it later. This brings us to step 3, which is to use vector d to parameterize a line through the heads of vectors n and p. Let's start off basic by setting some vector in R3, call it v, equal to t times our direction vector, where t can be any element of the real numbers. Visually speaking, what vector v does is that it takes our direction vector d and then stretches it out by a factor of t. In other words, t behaves as a scalar multiple. For example, if we let t equal 1, vector v would equal vector d. What this does is it takes vector d and scales it by a factor of 1. If we let t equal 2, vector v would equal 2 times vector d. We now have vector d scaled by a factor of 2. Likewise, if t equals 3, vector v would equal 3 times vector d. Now, if we let t equal -1, vector v would then be the exact opposite of our original direction vector. So far, I've been showing integer examples, but don't forget, we also have the freedom to plug in decimal numbers, such as, 1.3 or even 1.37. This is because t can be any real number. Remember, the real numbers include all positive and negative rationals, irrationals, and transcendentals. So now, let's consider the collection of all the possible vectors that you can form with vector v by plugging in all the possible real numbers. Doing this forms a line which passes through the origin. This line is also parallel to the line that we're trying to form. Hooray! We have now formed a line. However, we don't want it to pass through the origin. We want it to pass through the heads of vectors n and p. To fix this, all we need to do is add some vector whose head lands on the line we intend on forming. Vector n's head is on our intended line, so let's add vector n to our equation. What this does is it shifts our line up 1 unit, so that it now passes through the heads of vectors n and p. Therefore, plugging in various values of t should now produce vectors whose heads land on the line, just like how they did when the line passed through the origin. For example, when t equals 0, vector v would simply equal vector n. Also, for example, if t equals 1, vector v would equal vectors n plus d. This is also equal to vector p, and you can see why if you plug in the coordinates of vectors n and d yourself. When t equals 2, vector v equals vector n plus 2 times vector d. Likewise, when t equals 3, we have this vector. I hope you see it by now. The heads of all the vectors v were shifted up 1 unit and are now restricted to landing on our desired line. By speculating this diagram, it looks like when t has a value of 3, we overshoot the point q, and when t has a value of 2, we undershoot point q. So maybe if this diagram was actually drawn to scale, we could guess that t would possibly have a value of around 2.5 for where the head of vector v lands on the point q. However, this diagram is not drawn to scale, and we're dealing with arbitrary variables, so that guess should not be taken literally. Before we substitute Cartesian coordinates into our line, remember how I mentioned that in order to shift the line, all we needed to do was add some vector whose head lands on the line? This means that we could have added vector p instead of vector n if we had wanted. Let's rewatch what happened when we added vector n, this time with a stick figure. Imagine the figure pulls the entire line in the same direction as vector n. Now, what adding vector p does is that it shifts the line away from the origin by 1 unit, except now in the direction of vector p instead of the direction of vector n. This is another perfectly valid way of forming the same line. Heck, if you think like me, you may have even thought that if we had originally considered point Q to be a vector, we technically could have even added vector Q to form the same line because its head would also land on the line. This is true, however, doing so wouldn't be wise because remember, we need everything in terms of P for this forward function. So we have two choices in this step, which are to add either vector n or vector p. I'm going to choose to add vector n because it's the simpler option of the two. Let's now plug in the coordinates for our line. We're in R3, so I'm going to let vector v be defined by Cartesian coordinates x, y, and z. Therefore, our line turns into xyz equals 0, 0, 1 plus t times p1, p2, p3 minus 1. And this is where t can be any element of the real numbers. We're now on step 4, which is to solve for the value of t for where the line intersects the space being projected to. The space of which we're projecting to in this case is the xy plane at z equals -1. So let's let vector v equal xy -1. Therefore, our line turns into xy -1 equals 0, 0, 1 plus t times p1, p2, p3 minus 1. And this is where t is some element of the real numbers. When v equaled xyz, its head could have landed at any point along the line with various values of t. When v equals xy -1, this can only occur at one point on the line at one value of t, because the line intersects the plane at a single point. So here's what vector v now looks like. Once we set its last coordinate equal to -1, doing so restricted it to the plane, and we know that this occurs at some unknown value of t. Cleaning up the screen a bit. From here we get a system of 3 equations for the 3 Cartesian coordinates of vector v. The first equation is x equals 0 plus t times p1, the second equation is y equals 0 plus t times p2, and the third one is -1 equals 1 plus t times p3 minus 1. These equations then reduce to x equals tp1, y equals tp2, and -2 equals t times p3 minus 1. If we look at equation 3 a little closer, we can see that it contains the value of t in terms of p within it. That's just what we need, so let's reduce it even further. Therefore, from equation 3, we have t equals -2 over p3 minus 1. Factoring out a -1 from the numerator and denominator, we're then left with t equals -1 times 2 all over -1 times -p3 plus 1. The -1s cancel out, and we get t equals 2 over 1 minus p3. Cleaning things up, this finally brings us to step 5, which is to plug t back into the system of equations. Doing this gives us the remaining x and y coordinates for vector v. Plugging t back into equation 1, we get that x equals 2p1 over 1 minus p3. Plugging t into equation 2, we get y equals 2p2 over 1 minus p3. And as defined above, the remaining z coordinate of vector v has a value of -1. Since we know that vector v's head lands on point Q, these x, y, and z coordinates are really just q1, q2, and q3 in disguise. So we did it. We've now solved for the unknown Cartesian coordinates of Q in terms of P. Therefore, we can finally write out our function f of P equals Q. Hooray! I'll even put a little check mark next to what we needed to find in part 1 to indicate that it's been completed. We can now move on to part 2, where we'll be finding the inverse stereographic projection function. Alright, so I've broken up part 2 of this exercise into 5 main steps, very similar to the last part. To inversely project the point Q, our goal will be to find P in terms of Q. Step 1 will be to treat the points n and q now as vectors n and q. Here they are on the diagram. Step 2. Form a direction vector d with vectors n and q. This time, it must be between vectors n and q, not n and p, because we need p in terms of q. Let's now ask ourselves, what must we add to vector n to equal vector q? Well, it turns out we must add vectors q minus n to get to vector q. Now, we're going to let vector d equal this difference between these two vectors. Here's what vector d looks like on the diagram. As you can see, it's parallel to the line that we want to form, and its tail is position at the origin. As mentioned in part 1, we could have gone the opposite direction with vector d if we had wanted. Now, plugging in vectors q and n, we get vector d equals q1, q2, -1, minus 0, 0, 1. This then reduces to q1, q2, -2. Cleaning up the screen and saving direction vector d for later, we're now on step 3, which is to use vector d to parameterize a line through the heads of vectors n and q. To do this, we can once again start off by letting vector v equal t times vector d, where t can be any element of the real numbers. The collection of all possible vectors v then forms a line that passes through the origin. Adding vector n then offsets the line into our desired spot by shifting it up 1 unit. We could have offset the line in the direction of vector q by adding vector q instead of vector n if we had wanted. We'll now let vector v equal xyz, therefore plugging in vectors n and d, we get that xyz equals 0, 0, 1 plus t times q1, q2, negative 2, where t can be any element of the real numbers. We now have a formula for our line, and we know that the heads of all the possible vector v's are restricted to landing on this line. We're now on step 4, which is to solve for the value of t, where the line intersects the sphere. The general equation of a sphere in R3 is x minus x naught squared plus y minus y naught squared plus z minus z naught squared equals r squared. And this is where x naught, y naught, z naught represents the center of the sphere, and r is the radius of the sphere. Luckily, we're dealing with a centered at origin unit sphere. Therefore, x naught, y naught, and z naught equal 0, and the radius is 1. The equation of our sphere is thus x squared plus y squared plus z squared equals 1. Many people like to teach stereographic projection having the radius of the sphere equal to a half, the south pole placed at the origin, and the xy plane at height z equals 0. So be careful for examples like those in this step. Alright, so if x, y, and z equal what they do in the formula for our line, and if the sum of the squares of x, y, and z equal 1, if both of those are true, there are at most 2 possible positions where vector v can occur at for where the line intersects the sphere at 2 values of t. Here are those vectors on the diagram. One is where vector v equals vector n, and the other is where vector v equals vector p. Trivially, the line intersects the north pole at t equals 0. However, the other value of t is not so obvious. Cleaning up the screen a bit, from our line, we get a system of 3 equations representing the 3 Cartesian coordinates for vector v at various values of t. Equation 1 is x equals tq1, equation 2 is y equals tq2, and equation 3 is z equals 1 minus 2t. So if these are the x, y, and z coordinates of vector v, and if the sum of their squares equals 1, to see where our line intersects the sphere, we must plug these coordinates of our line into the equation of our sphere and then solve for t. Therefore, tq1 squared plus tq2 squared plus 1 minus 2t squared equals 1. From here we should expect 2 solutions to this equation, one at t equals 0 and another at some unknown value of t. We can then expand this expression out to t squared q1 squared plus t squared q2 squared plus 1 minus 4t plus 4t squared equals 1. Getting all the t squared terms on the left hand side, we now have t squared q1 squared plus t squared q2 squared plus 4t squared minus 4t plus 1 equals 1. Canceling out the 1's and factoring out the t squared gives us that t squared times q1 squared plus q2 squared plus 4 minus 4t equals 0. At this point, it's easy to see that t equals 0 is a solution, as expected. Reducing even further and moving the 4t to the other side, we get t squared times q1 squared plus q2 squared plus 4 equals 4t. Canceling out a t from each side and then solving for t finally gives us that t equals 4 over q1 squared plus q2 squared plus 4. These are the 2 values of t for where our line meets the sphere. Finally, step 5 will be to plug our values of t back into the system of equations. Plugging t equals 0 into equations 1, 2, and 3 gives us x equals 0, y equals 0, and z equals 1. Therefore, this just further shows that our line meets the north pole once at t equals 0. Now, plugging in the remaining value of t into equation 1, we get that x equals 4q1 over q1 squared plus q2 squared plus 4. And now into equation 2 gives us that y equals 4q2 over q1 squared plus q2 squared plus 4. And then into equation 3 gives us that z equals 1 minus 2 times 4 over q1 squared plus q2 squared plus 4. If we take a look at our value of z, we see that it can be cleaned up a bit. Forming a common denominator out of the 1 and multiplying the 2 and 4 together, z then turns into this expression. This expression then reduces to q1 squared plus q2 squared minus 4 over q1 squared plus q2 squared plus 4. We know that these x, y, and z coordinates belong to the vector whose head lands on point P, therefore they really are just p1, p2, and p3 in disguise. So we've now done it. We've now solved for the unknown Cartesian coordinates of point P in terms of point Q. Therefore, we can finally write out our inverse stereographic projection function, g of q equals p. I'll now put a check mark next to what we needed to find in part 2 to indicate that it's been completed. And this now brings us toward the end of the video. Hello there, thank you so much for watching my video. This is the first time I've ever made anything like this, so I hope you enjoyed watching it. There is one favor I'd like for you to do, and that favor is to stereographically project your finger or mouse, whatever you're using, onto the like and subscribe button, and then click or tap on both of those. Some of you may have been wondering why I didn't mention anything about topology in this video, and the reason for that is because I wanted this to be strictly geared towards how to find the function for stereographic projection. However, I do plan on making more content in the future that will cover stereographic projection from a more topological viewpoint. For example, I'd like to talk more about what is referred to as the point at infinity. If you look at the forward function from part 1, and if you plug in the coordinates of the North Pole, it turns out that you get a divided by 0 error. So we can't actually project the North Pole until we declare some topological rules. And if you know anything about continuous functions, think about what this divide by 0 error means in terms of continuity. Last, but definitely not least, I'd like to share my main motivation for creating this video. Because this projection can be done in higher dimensions, this means that we can project the hypersphere, which is naturally embedded in 4-dimensional space, down to the entirety of 3-dimensional space. I believe this is very useful because it allows us to see the hypersphere's Hopf fibers in a very meaningful and powerful way. This now wraps up the video, and I hope you have a wonderful rest of your day. Alright, I think that's good.
One final take?
Like all the way through?
Like that last part?
Fine.
No, you don't have to.
I thought it was decent.
Same.